Hello.
Hey, hi Amit. Hi Ratna.
Hi. Hi.
Hi.
Hi. How are you all? How was the week?
Good.
Good.
So, did you attempt these questions and did you read the fourth chapter?
I fell sick during the week, so I couldn't do much.
Okay.
Yeah.
Yeah, no issues.
Yeah, so I just read a bit, especially chapter 4, especially the last section, and problems I was just trying to solve, but I couldn't put it all on that GitHub, Word doc, but I pasted it last night, so I'm thinking that today we will talk. But I think if everyone is interested, they can go over um, in the upcoming days whenever they get time, and as and when we meet every Saturday, we can discuss. Like it's not. I mean, even if we are in some future chapters, we can always talk about a few questions from the past chapter.
Yeah, surely. Because we'll be coming up with uh like different things along the way, right? Because machine learning is based on probability. So while doing machine learning, we would be thinking, okay, why is this like why are we taking it like this? Or when we do something related to Bayesian, we might have questions. So yeah, throughout the reading, we will have questions. So yeah, we can revisit the same problems. We could revisit, or we could come up with new questions as well.
Yeah, absolutely. Yeah.
It could be like this, where if someone has a question later in the future, at the end of the session, they can come up and say, hey, I've been trying to look at this and I have a doubt regarding this. Can we try to look at it in this time in the last 5 minutes, and we can take a look at it and see if we can help that person out, something like that.
Yeah, absolutely. Yeah.
Yeah. Actually, the last part, that is KKT and example of least squares, I was not able to do. But I have read it once, but it was like 1 month back. I am familiar with it. Uh, let's see how it proceeds. And I was thinking of taking this session in a question answer format, but I think I'll just if there are some doubts, I think I can just hover over all the textbook, the PDF ones, and if there are some doubts, we can discuss. So let me just present my screen. Is my screen visible? Uh, so okay, so I'll just proceed and like very quickly, and like if you have doubts, we will just focus on those aspects. So numerical computation. Yeah, so first we see overflow and underflow, right? And so, uh, do you guys have any example uh, of common overflows and underflows that you see? That you come across in program in general?
Binary search, right? When you're calculating the mid value. you
Yeah.
calculate differently. You don't just do low plus high if you're taking two indices, which is 0 and the end value of the array, and you can't just add them up and divide by 2, right? You have to do low plus high minus low by 2 to prevent.
Yes. So if there are like two values very close to the maximum possible value,
Yeah,
and we cannot just do L plus R by 2, because then L plus R is uh, this will overflow. So instead we can just do L plus R minus L
minus L by 2.
by 2.
Yeah.
Yeah, this is a good example. Yes. Yes. I think regarding underflow, we come across fractions where the denominator goes close to 0, and so something like 1 upon n, where n goes to very close to 0. That time we put a threshold on, and like if it is less than some particular value, say 10 to the power minus 6, we can just take 10 to the power minus 6. So in those cases also we approximate. Any other example? Okay, so let us proceed. Okay, so then we had softmax function here, and so here they discussed, there's a line which says simple algebra shows that value of softmax is not changed analytically, right? So what they are doing is, instead of calculating softmax directly, they are converting this xi variable to a new variable, so that uh, the values won't be very large or won't be very small. So
Can you repeat that? Sorry.
yeah, so here if all xi's are same, then softmax is like 1 by n, right? It's like 1 by n. So now if c is very negative, then e to the power c will underflow, right? So if c is like very negative, let's say like 10 to the power 20,
Yeah, underflow, correct.
yeah, so that will be like, this will be like kind of 0 by 0, right? And so in that case, there are some errors in computation. And if C is like very large, then again uh, it will overflow. So am I right?
Yeah.
Yeah, I think because what they have done is they have subtracted from maximum value, which means if it is maximum, it becomes 0.
Okay. Yeah, now I
Right.
get it. I didn't see that z equals x minus max of x.
Yeah, yeah.
Okay, understood.
Yes. Then okay, there are some things also discussed about log, softmax, and all. Like if you guys have questions in this, just do let me know. Then there is poor conditioning. So condition number of a matrix is this quantity ratio of its maximum eigenvalue or minimum eigenvalue, absolute values. So when this number is large, matrix inversion is sensitive to error in the input. So can anyone visualize this? Like, why is this true? So like if we have seen that every matrix is a transformation, right? So if we have a circle and it gets transformed into an ellipse, right? So here you can see in some particular direction it is stretched a lot, and in some particular direction it is stretched very less. So this is the direction corresponding to like lambda max, and this is the direction corresponding to lambda min. Now if if A is a matrix which is doing this, then any input vector. So if initially this input vector had this output, if we just change this input vector by a small amount, right? Let us say, then this might get changed a lot in magnitude as well. So a small change can lead to a larger change in the output. Small change in input can lead to a larger change in the output.
So this new yeah, I think this intuitively also makes sense. So that blue vector that you drawn, we are
Yes.
expecting it to be very small, right? To have that similar larger change. If so, intuitively, if you think, if we move that blue vector on your left hand side, like that's the input vector, if we make
Yes.
it far from the black vector, which is our eigenvector actually. So if I make it far, let's say orthogonal, so that means that now the transformation will make the least change. Exactly right. So so the more closer I am with that, so that's why that delta change,
Yeah. Yeah.
I'll still get that max transformation.
Yes. Yes.
And the more
Yes.
I far away, I mean, go far, I will, the maximization, gets reduced basically. So, and that also we can see from the input space, that blue vector and black vector. If the dot product between those two is very high, so then that means they are very close to each other, and we can say that the transformed vector will be also very close to each other, like in that sense.
Yeah. 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 Yes. So like I think in equations like where ax equals to b, then we have x equals to a inverse b. And now A inverse is like, I think, like from the uh, what was it, eigen decomposition. And here we have like 1 by lambda values also. And now, practically speaking, if there is a small change in uh, our b value, this will also affect the x value here also. So, uh, so there is 1 by lambda which is affecting like the reciprocal, and there is also this lambda max by lambda min which is affecting. These both are affecting. So, particularly by calculating inverses, which they have mentioned here, like matrix inversion. So the smaller lambda values won't make sense. And if B is in the direction close to like this direction, then B will get transformed more, but I mean stretched more. But if it's in direction this, then it won't get stretched more. So yeah, I guess this is the condition number of a matrix. Then we have gradient based optimization. So we generally focus on minimizing an objective function, and if we want to maximize, we just use minus f of x, and we minimize the negation of f of x. So yeah, so any doubts in this like part, like critical points, stationary points, uh, local minimum, local maximum, saddle points? I think like everyone is pretty much clear with this stuff. Uh, okay. So global minimum is the minimum across all possible input values. It is the minimum of f of x over all the possible x values. So it can be possible that our algorithm, you know, converges into a local minima, and it's very difficult to get out of local minima. So okay, I had a question. Can you think of uh, an example where if we assume the function to, for example, if the function is, let us say, so let us say y equals to f of x, so a single dimensional function, and it's something like this, right? And now here in some cases we can see that if there are constraints, like here we can see the minimum value of y is tending to minus infinity, but we have some constraints, right? Like for x, that x is from, let us say, some from L to R. So within that range, we have to find what is the minimum value of y, and in that case, we would have an answer, and it would not necessarily be that uh, that its derivative is 0. So we would have, in some cases, extremas which are not necessarily a critical point. Okay. Yeah. Then we come across partial derivatives when we have multiple dimensions and we want to calculate gradients in a particular direction. We have directional derivative. I think this was a doubt of Andrea. So here it is mentioned that direction derivative in direction u, which is a unit vector, is the slope of function f in direction u. In other words, directional derivative is derivative of the function f of x plus alpha u respect to alpha. Now it's with respect to alpha because you can alpha is the distance traveled in that direction. You can also uh, you can also write alpha u is nothing but you can say xu. So it's like how much distance is traveled in u direction. So it's kind of del by del xu evaluated at alpha equals to 0. So that is generally the case. We take derivatives when we want to find infinitesimal change in the values. So, and using the chain rule, we can see that this evaluates to u transpose gradient of f of x in x direction. So that is so u transpose f gradient is, so gradient of f of x is nothing but this vector del f of x by x1 del x1 del f by del x2 and so on. And its dot product with u is nothing but u transpose system. So yeah, so you can think of uh, gradient as gradient is the maximum possible deviation that can occur. So what is the maximum possible deviation that can occur in uh, I mean, what is the deviation that can occur in first dimension, that is del f by del x1? What is the deviation occurring in that can occur in second direction? Okay, so why it is a maximum? Because generally these dimensions are independent of each other. So if one in one direction this is the change, we can also go in another direction uh, with second change. So if we choose a direction which maximizes this, we can also go in direction which maximizes this because they are independent. If they were dependent, if we would go in one direction, we were we would not be able to go in second another direction. So gradient of f is generally the maximum change that is possible. And when we do u dot this vector gradient of f, It is the maximum change that can occur is component along the u vector. Component of max change along u vector. So that is u transpose gradient of it. So this is the directional derivative. And if you want to minimize this, we can just take the norm. And since we are taking u as unit vector,
Can you hear me?
yeah.
I think I'm just missing the because they say using the chain rule. I think I'm missing the I
Okay.
think I'm missing the chain rule. But I guess here if you do the derivative, what do you say, on alpha, then you get u, and then I don't remember what's the rule, but then you need just remember the chain rule, but then you need to multiply it by the derivative of the whole expression, right? There's something like that. I'm missing this piece, but
Yeah. Yes. Yeah, actually chain rule is confusing, but I think for chain rule they are probably saying because uh, there can be I mean x is dependent on several other uh, dimensions or independent variables. I mean f of x plus alpha. We are just taking uh, del alpha. But the overall intuition that comes out to be is like the gradient is the maximum along. Uh, it will give the direction in which the difference is the maximum.
okay.
And u transpose gradient is just taking the component of it. It's just dot product of two
Mm,
vectors.
yeah.
Yeah, yeah. For the chain rule part, I think I'll write it somewhere again, and so we can discuss it later. It's similar only. It's not a different one.
Okay.
Okay. Yeah. Yeah. Feel free to jump in between because I am not able to see the chat of Zoom. So uh, if you want to minimize this gradient, uh, then we can see that uh, here u is unit vector. This will turn out to be 1, and I think this is also unit vector, right? This okay, no, this is not dependent on u, so this will just come out. And cos theta just remains. Cos theta is the angle between u and the gradient vector. So to minimize, cos theta should be -1. So angle is like 180 degree. It's just opposite of u. I mean gradient. So if u points opposite direction to the gradient, we get the minimum value. This is again intuitive because Gradient gives the maximum change. If you just go opposite to maximum change, you'll get minimum kind of change. I mean, in the negative, maximum change in the negative direction. That is minimum. Okay.
Yeah, just one small thing to what you mentioned. I think uh, this whole directional derivative thing. So what I felt was it is something like this intuitively is, let's say we have a function y equal to, let's say, x square. Okay, it's just a uh, one variable function, right? Y equal to x square, right? And if you can now draw an x and y coordinate, yeah, right, x and y coordinate. If you can draw, Amit, that would be helpful. Just like in x-axis and y, yeah, right. So now this x square is kind of a U shape, right? So here, this is in 2D, but the function that we have is just one dimensional, right? So now if you want to find this minima or maxima, it doesn't have maxima but minima, all we need to do is we just need to find the derivative with respect to x, right? We find the derivative with respect to x-axis. So it's just on one direction, right? So we can go only in one direction. Now let's say we have another function where we have two variables, multivariate function. Let's say z equal to x plus y, something like that. It doesn't matter. Z equal to x plus y. Now here we have two variable, and now if we have to plot, we have to have three axes, two as a variable and z as the output. Now in this case, if you have to find the maxima or minima of any function, whatever that function is, in this case x plus y, what we have to do is we have to do partial derivatives. Now when we do partial derivative, what we are doing is essentially we are restricting ourselves to just move in one direction, keeping other directions as fixed, right? Just in one axis, keeping other axis as fixed. But if you look at this plane, XYZ plane here, we can come to a certain point from multiple directions. Like there are infinite many directions I can come to that point. There is not just one single, if you just pick any point, if you can just draw one point in this plane, and yeah, so in this point, I don't know because the whole idea of this calculus and everything is I have no view of what is happening surrounding to this blue point, right? I don't have any view how that function looks like, a 5 units ahead or 5 units back, right? I don't have any access to visibility, right? Exactly. So in this case, what partial derivative gives us is just the measure of change in a certain direction, one direction, keeping all other direction as frozen. So the question that people asked is, uh, I can move in multiple directions, right? There are infinite many directions. What is the right direction I should move such that I go to the maxima or minima? And gradient only gives us that direction. And that direction is nothing but a linear combination of this x and y. And that's why that u vector that we are talking about. And since we just need the direction, not the amplitude, that's why we consider u as just always a unit vector. So the question that we were asking, why we are even going to directional derivative is with the fact is that we need to find, since there are infinite many ways, many directions from this blue point, I can go to the next point. But my objective is to go to the maxima or minima. So who will guide me? So this directional derivative will, as Amit mentioned, it will give you the right direction where you can go take to the maxima, or if you take the negative, it will be minima, whatever it is. But that is the value. Otherwise, partial derivative we already know. So partial derivative is like if I'll just send you an image on Slack. I'm just sending so that it remains there. So I'm just sending one. I just send an image if you can see that. What I mean by Yeah,
Okay.
if you see this image, this is what a partial derivative is. So this is this is similar to that x, y, z, right? This is a 3D plot. And if you see this, the first one is I have kept y constant. So that is, you can think of it as a partial derivative with respect to x, right? And in the next image on the right hand side, I have kept x constant, right? So that is basically partial derivative with respect to y. But if you think about that purple point, uh, with just partial
Yeah.
derivative, I am restricting myself to either x-axis or y-axis. But if you look at that purple point, I can go to any direction in that whole hill kind of a thing, right? So that function, I can go from any direction. So that any direction is defined by that unit vector u, which is a linear combination of this x and y. And that's what this directional derivative gives us, that, okay, go to that direction. That is the right direction. There are infinite many directions, but go to that direction. So that is the intuition I got, when I looked at this.
Yeah. Yes. Yes. Actually, like in every direction there is some change, and if we want to find the direction with maximum change, we can just take all these changes and consider. So if in for 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 x direction we have some change that is going to happen in 3 units. If in y direction there's the change is going to be happening by 4 units, then we know that if we move along like this direction, we can get this change in just one shot. So uh, it's like,
Correct.
yeah, so it's like that is what gradient is like. It's the maximum change that is possible at a given point. Great, great. Okay. Mm, so yeah, yeah. So we just have to go to the opposite direction of the gradient to minimize the value, right? And this is also known as this approach is known as method of steepest descent or gradient descent. And by what amount should we go? Because we are performing, we are evaluating in a discrete manner. We want some uh, quantity, the step size to take in that direction. So that is epsilon, which is also known as learning rate. And so they have talked about line search, where we can uh, see what epsilon to choose by doing hit and trial over several epsilons and checking where it is best. This step size is best. Okay. Another way is to analyze the function mathematically and jump to the critical point directly. Now for this analysis, we are proceeding further. So they have introduced Jacobian matrix, which is uh, so if we have like function where the output is also n-dimensional and input is m-dimensional, then the ijth element of the matrix is this del pi del xj. Xj is the jth input variable, and f of xi is ith output variable. So this is the Jacobian matrix. Then this is again the first derivative. Now we come to second derivative. So
So
where,
if I just
yeah,
the time the difference between the gradient and the Jacobian is the output of the the function, right? The number of dimensions, right?
Yeah, yes. So I think if you see del f, like I'm saying fi for fxi and del xj, this is like ijth element of the matrix. Now if you see del fi and del xi, right? So will this be gradient of, I mean, fi with respect to xi? So actually not necessarily, I guess. It's not necessarily, probably, because I just thought it in this manner, but I think output is entirely different from input. So gradient means that uh, gradient is with respect to a particular uh, 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 we have a function and we have a vector x, right? But here we have n functions, kind of. Since we have n functions, and so each function will have its own gradient.
Yep,
Am I right?
I think so.
Yeah.
Yeah. Yeah. So we are just representing this in a matrix where we are not adding it. Unlike, so sorry, yeah. So we are just representing these values in the matrix, and we can perhaps add it, or row wise or column wise whenever we want. So here these are the dimensions, and these are the functions, n functions. So I think a column will represent one gradient, I guess. That would be the case, probably.
Yeah. Right.
Yeah. Okay. So then we talk about second derivative. Second derivative is like curvature, and they have discussed if second derivative is zero, then there is no curvature, right? It's flat. And so they have shown this nice diagram also here. So if second derivative is zero, it's kind of flat, and after this, the slope is going to decrease. And if the second derivative is if the second derivative is zero, then there is no curvature. And if there is negative curvature, means second derivative is positive. Right. So which means that am I correct? I think I have written it opposite. Yeah. Yeah. So if the second derivative is negative, which means the derivative will be decreasing. So if like this is the derivative, at some point later, the derivative will be lesser. So if you see it in theta, this theta, so if it is, let's say, 135 degree, this theta will be like 160 degrees. So it's like more negative. The tan theta will be more negative. Instead, if you see here, we have this theta, and whenever you go ahead, you will get tan theta will be greater. Right. Or in simple terms, if we go from left to right, you always have to take right turn here. And here we have to take left turn. Here no turn in middle. Okay. Now whenever the function is continuous, partial derivatives are continuous, and the differential operators are commutative. That is, hij is equals to hji, where H is the Hermitian matrix. A Hermitian matrix is defined, again, the ith element is jth, directional derivative of f along the jth variable, and then along with the ith variable. So that is ijth variable. Now, generally, practically speaking, Hessian matrix is symmetric, and since it is symmetric and real, its eigenvalues and eigenvectors are also real, and eigenvectors are orthogonal. So it is symmetric only due to this reason, because if the partial derivatives are continuous, which generally we assume they are, that is why it is symmetric, and it is obviously real. So okay. Then second derivative, the specific direction represented by unit vector is given by d transpose ht. Yeah. Can anyone see why this is the case? This line, second derivative in a specific direction, is given by d transpose ht. So d transpose hd is like, you have some direction here, you have the Hessian matrix, and you have the directional vector here, right? And here ij uh, element is del f by del nj del xi, I guess. So it is, when this will be multiplied by This is again uh, cross. This will be multiplied with this vector to give this value. Has anyone seen this? Like, why is this the case? Why is B transpose? Why is this the directional uh, derivative? Second derivative, sorry. Second derivative in a specific direction. Hmm.
I was wondering the same thing also when I read it. But I don't know. Is these the unit vector, right? So it's something like 0, 0, 1, 0, 0 something. Is that correct?
Okay. Okay. So if we like, let us say assume it's like 1, 0, 0. I mean, if we just take a particular direction, because I mean, it can be non-zero, but in this case, I think here the values, these values, they will get added up, right? And so their summation will be here, and we'll get the sum of, so these values are like del by, again same thing, del f by del x1, the x1 variable, xj.
And since it's 0 everywhere except in one dimension, you get only the, say in this case, the first one, right?
I think we'll get some, right? Achha, sorry, yeah, sorry, my bad. Yeah, yeah, so we'll get
It will be
only,
just the first column.
yeah. Just sum of this. No, this will be multiplied with this. Okay, this entire column will be there. Right. And here we'll get only the first element. Am I right?
Yeah.
Yeah. So if this is the direction, we are getting only the first element of the Hessian matrix. So, but I think it will turn out to be, I think it is a dot product of some sort, but I'm not able to visualize it right now, like, because it was easy to visualize this thing. But yeah, I mean, like, this is the second derivative in that direction, and this was the first derivative, right? This was the first derivative in the rest of the system. Yeah. Any idea, or like you can just proceed further and come back to it later?
Yeah, I have not read through this section, so but I got some. I mean, I'm getting some intuition as you were explaining. So I'll check that, and if I find anything, then we can discuss later.
Yeah, yeah, we can discuss it. Yes. So okay. Then they have mentioned for other directions of D. Yeah, if D is an eigenvector of H, then second derivative will become the eigenvalue, right? Which is, you can just replace HD by lambda D, I guess. Then D transpose D will be 1 because it's eigenvector. So it will be lambda, second derivative. But they have mentioned that for any other direction, the directional second derivative will be weighted average of the eigenvalues. And weights are from 0 to 1, which means if lambdas are, so this is lambda min and lambda max. Let us say this is 3 and this is 10. So the second derivative will always lie in between this range. It cannot go here. It has to be here. Yeah. Any idea? Anyone has any idea? Otherwise, I'll come back to this later. Okay. I'll try to prove this and try to put it in the Google Sheets, or even in the Google Doc in the question bank as a separate question. Okay. Then we have seen that we can approximate f of x by Taylor series expansion, and let us say we have this value f of x naught. We want to optimize f of x. So this is the approximation, and if we replace x by x naught minus epsilon g, where g is the gradient, then this will turn out to be this equation here. Yeah, so in this equation we have like original value of the function, which we have already calculated. Then this is like the expected improvement that we are going to do in this. We are going to minimize it more, and this is this correction factor, which is the third term. They talk about this factor becoming, if it is 0 or negative, then there is no matter what, if this is always negative, G transpose Hg, then this will always go towards optimization. I mean, always minimize because it is being subtracted by a positive value. So if we increase epsilon by a large quantity, even then our function f will minimize. But if G transpose Hg is positive, then we get this optimal step size, which decreases Taylor series approximation, right? So, any idea how we got this from the above expression? I guess if we differentiate with respect to epsilon, I think we'll get G transpose G and minus plus the 2 will get cancelled out, and epsilon G transpose H G equals to 0. If we do it for a critical point, then we'll get epsilon this, which they have shown. Right? So it's like I think we have to differentiate by epsilon. Okay. Yeah, in the worst case, as they said earlier also, lambda max, if G aligns with the maximum eigenvalue, that is the worst case, right? Then G aligns with the eigenvector corresponding to maximum eigenvalue. And step size is 1 by lambda max, because this is 1 here, and this will be lambda, right? Because this is again lambda G transpose. Okay, so this is the reason they are saying that eigenvalues of a Hessian matrix determines the scale of learning rate. So if we are going in the worst case, it will be 1 by lambda max. Okay. Okay. Do you have like any doubts in like this sections here? Can just proceed. So they have talked about saddle point, local maximum minimum, and yeah, if f double dash is less than 0, it's a local maximum. It's greater than 0, it's minimum. But if it's equals to 0, then we cannot conclude it that it can be flat, it can be a saddle point where it is 0 with corresponding to one of the axes, but along some other axis it is not maximum or minimum. Or it can be maximum with respect to some axis, minimum with respect to other axis. Right? And then if Hessian is positive definite, then we have local minimum. And if it's negative definite, we have local maximum. Right? Uh, okay. I mean, if one of the eigenvalues is 0, then the test is inconclusive. Otherwise, you can just see the Hessian and conclude whether it's a local minimum or local maximum. So if you have a curve, if you have f of x, the objective function, and you are at some point, some x, which is a vector, and you want to find whether it's optimum or local minimum maximum, you can just compute the Hessian matrix. But in cases where it fails, it can be also the cases where the condition number is large. If the condition number is large, in some directions the function value will change a lot. In some other direction it won't change much. So mm, yeah, gradient descent is unaware of change in the derivative, right? So this is about conditional number. It is difficult for the gradient descent because, as we discussed earlier, like there are no eyes to see what is happening or to visualize. So you want to interpret it mathematically, and uh, yeah. Now, poor condition number also makes step size difficult. Choosing the step size difficult, can be overshooted, right? So they have given an example also here. In this example, you can see we have a function whose condition number is 5 at some point, x. This means that direction of most curvature has 5 times more curvature than the direction of least curvature, right? So curvature is like, this is the curvature. Yes, someone was saying something.
No, just saying yes, right.
Yeah, yeah. Like curvature is like this. This is the curvature, right? Uh, so in this case, the most curvature is in direction 1 1. That is this direction. Am I correct or what? Is this correct? Because the most curvature should be in this direction, right? 1 minus 1.
I think that the most curvature is the how do you say? Not in the shortest. Your first blue. Okay.
Okay.
The
Is it this one? Or
oh,
I mean, by curvature, are we saying the stretch that we are creating, or the curvature of the function? Like, I think, like generally we depict curvature by, like, for example, what is the curvature at this point is the radius of the circle, the smallest circle, which is like tangent. If we go above, it's like a bigger circle, with bigger radius. So it has more curvature. If we have line, it's like circle with infinite radius. But
I
am I
think the
missing
rate,
something here?
I think the rate of change is, you have an kind of ellipse. The rate, I can't draw on this thing, but how should I say? In the diagonal between x1 and x2.
Yes, this one, right?
I would say the other one. I think this one is more
Okay, this
gentle.
one.
Yeah, I think. Am I saying it wrong?
Yeah, I mean, like, it is stretching a bit less here. I mean, generally, if it is stretching more, this is like lambda max, and this is lambda min rate. And and if it is stretching less, okay. Oh, okay, okay. Epsilon was uh, curvature is the value of second derivative, right?
Oh, but actually, it's written. It's in. Yeah, they say the most curvature is in direction 1, 1. So yeah,
Yeah, yeah. That
the
is what
least in
is
1,
confusing me.
-1.
Yeah, that is a bit confusing. I mean, like, you see this direction. This is one direction, right?
Yeah,
But it is like, don't you think it is like least curvature in that direction?
I think you need to see it in like in 3 dimension, right? You have this kind of
Okay,
ellipsoid stuff in
okay,
like the volume you would get, and uh,
okay,
the rate of change is uh,
okay, okay.
you need
Mm,
you need less. You need to move less to to get. It depends if it's up and down, but to get to the maximum point in dimension 1, 1. Instead, the ellipsoid is kind of stretch in the other direction, 1, -1. You have more time. You need uh, for the same amount. You need more steps to get to move to move of
okay.
the same amount, right? It's hard to explain
Yeah,
just
I
with
mean, it's a bit, it's a bit confusing, but I think something like that, as you said, perhaps it's something like that. So, like, okay, what they are trying to say here is, suppose 1, 1 is the direction where there is most curvature, and 1, -1 is the direction with least curvature. Then, if we blindly follow the direction with most curvature, right? So a gradient descent uh, wants the maximum gradient, right? They are saying gradient descent wastes time repeatedly descending these walls because They are the steepest feature. Since the step size is somewhat too large, it has tendency to overshoot the bottom of the function and thus needs to descend the opposite canyon wall on the next iteration. Yeah, I mean, like in this direction, it is very step size will be large because we'll go and but for this direction, the one which they have shown, it's kind of oscillating.
Yes, because it wants to move in the direction of more curvature, right? So it kind of
Like
and it is more
here we
steps.
are relating the first derivative with second derivative because we are trying to analyze second derivative and the gradient descent will move along the first derivative, like wherever it is maximum, right? Now the connection between two is this Hessian matrix and the eigenvalues. So
I think that's why later in the chapter they say uh, there are other methods to go directly in the, if I remember correctly, to go directly in instead of doing this jumping around. It can take advantage of the Hessian matrix.
okay. So, actually, like I am not able to understand why it is jumping around. I mean, uh, it's technically going in the direction of lambda max, which is fine, but the oscillation thing is a bit. I'm not able to understand right now. Okay. So let's proceed. Let's come back to it later. I mean, like there are so many doubts which are remaining, but I'll try to sit and complete them, solve them. Great. Okay. So they suggested another method, that is Newton's method, because whenever there is poor condition number, as was this in this example, uh, the Hessian matrix test is not able to solely guide us for the search. So in Newton's method, we are not approximating this by epsilon g, which was kind of linear. So yeah, we solve for critical point of this function, which is this, by I think differentiating again. Then okay, so we get a for every point we get this x star point, which we can where we can calculate the f of x again, right? So if we have x naught, we can then go to x star, and when f is positive definite, Newton's method, when it is applied, we can jump to the minimum of the function directly. When f is not truly quadratic but uh, can be approximated as positive definite quadratic, again we can apply this multiple times. So I think like this is the main approach which is discussed in this book. Mm. Okay, this is a useful property near local minimum, but it can be harmful near a saddle point. Uh, why is this the case? Can anyone figure it out? Like Newton's method is iteratively updating the approximation and jumping to minimum of approximation can reach the critical point much faster than gradient descent. But this is a useful property near local minimum. It is harmful near saddle point. So again, like this is also one of the route. I think again this is like again oscillation stuff here, but not sure right now. Okay, Newton's method is appropriate only when critical point is minimum. That is, all eigenvalues of Hessian are positive. Whereas gradient descent is not attracted to saddle points unless the gradient points towards them. Yeah, I have to I think reread this part. But if anyone has knows this, please jump in to uh, help us understand. Otherwise, you can go ahead. So here they have discussed first order and second order optimization algorithms. It's like gradient descent and Hessian matrix and Newton's method. Now they see that deep learning algorithms tend to lack guarantees because family of functions used in deep learning is quite complicated. Okay. We talk about Lipschitz continuity, which is bounding our uh, derivatives to with some constant L. So our change in the function will be, I mean, we can ensure that whenever there is small change in input, there will always be small change in output. So, and we can create Lipschitz continuity by some minor modifications in our actual objective functions. Now, they also talk about convex optimization. It's not much mentioned here, but since convex functions have positive semi-definite Hessian matrices, uh, uh, it is very easy to calculate local minima and global minima. But most of the deep learning problems that we encounter, their objective functions are, I mean, not convex functions. So this theory is generally not that applicable in deep learning. Yeah. Constrained optimization, like I haven't gone it through yet, like yesterday, I mean this week. But do you want to, like, does someone wants to take over, or like I can just, if you have some questions, I can just uh, discuss it. Or we can go also to the questions, some of the questions.
Yeah, I have not gone through that particularly for this section, but maybe we can discuss later on. But I don't have any specific questions on this, and I don't think even if I've read, I would have understood. But yeah,
Yeah, I mean, only 2-3 pages, but actually I wanted to understand this in depth. I actually missed out some of the concepts in Hessian matrices, second order derivatives, but I think I'll try to write them as doubts and try to solve them in our Google Doc later on. But I think
yeah,
like yeah, yeah, yeah. So probably we can do constraint optimization in the next session, and
Y-
right now we can just do some questions, look at some questions that we uh,
Yeah.
that are there in the book.
So,
Yeah.
yeah, sure.
But
So I think, yeah, go ahead. Andre. Go ahead, Andres. I think you had something.
Yeah. Yeah.
Okay,
Yes,
so
Andrea, you're saying.
okay, so what I was saying is, I think one of the thing which was not covered here is, I mean, they have uh, not touched upon is this Taylor series expansion, and
Yeah.
I felt that Taylor series expansion understanding can actually
Okay.
intuitively clarify
Yeah.
a lot of things in function approximation. So when I looked at the when I took one example and I was just plotting that, and I was just expanding each term, and I was getting the similar function to the function that is in question. So I think one week, whenever I mean, it's not nothing to be in next week, but
Okay.
we can discuss a little bit on Taylor series expansion, because that will connect a lot of things what we are discussing now, like function approximation, why to stop at second derivative, why not to stop at, let's say, 10th derivative. It will always approximate better. But a lot of intuition might get cleared if we just spend some time on purely on
Okay.
Taylor series expansion.
Yeah. 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 I mean, like Taylor series expansion is generally how people, what I understand is that how people created Taylor series in the first place was they were trying to approximate functions by uh, polynomials of their own properties. So that includes their derivatives. So now, if you want function to be represented by derivatives, they somehow proved that this is the Taylor series of the function. And I think for the errors which get uh, magnified as we go in the higher order, because we had like an epsilon square right here, like uh, here you can see this part.
Yeah,
So like as we go to the right, we would get a like epsilon cube, epsilon to the power 4. And since we want to uh, keep our epsilon very small, the step size, it might those terms might end up uh, uh, I mean tending to be very small, which can be neglected. But yeah, I mean, like there has to be how to fixate on which uh, where should we cut off this thing. And I think what they have mentioned in this book is that every function is generally approximated by quadratic functions. It's easy to approximate any general given function with multiple quadratic functions. And since we are dealing with quadratic functions, they have not gone to, I think, the third derivative. I mean,
yeah,
but yeah, I mean, like in every aspect, if you like see, there is a lot to explore. But uh, let's see how we can uh, get time to read all the mathematical stuff as well as go ahead with the machine learning and the architectures ahead.
Yeah.
And
You know,
whatever
this
what
constraint optimization is just a few pages, right? It's actually a whole book. But
exactly.
yeah,
yeah,
difficult topic also.
Yeah, absolutely.
yeah.
Yeah.
But like what I like about this book is whenever I read a single sentence, right? I always get some you know, thoughts where I can brainstorm. Every sentence is like it's really good. So it
Yeah,
just keeps me thinking, okay, why have they included this? And what, yeah,
yeah. This this whole book is an index of all the books on this planet. So every line is actually a summary of another book somewhere in the vector space of books.
yeah,
Exactly.
yes, good example actually.
Yeah, it's like every line has maximum entropy.
Yes.
Yeah, yes. So like let's do some questions, I guess. So should we which chapter you want to do? Like I have not written any questions for introductory chapter, but I think linear algebra, some of the things like I uh, wrote these questions which we already discussed, but if you want to rediscuss them, I'm happy to do that.
I
Uh,
actually didn't get the chance to like
solve
see
this.
through
Okay.
these questions and solve it. So yeah, I don't have any inputs for today at least. Maybe next session I'll have some inputs from my side.
Okay. 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 So okay. We can solve like uh, some questions if you want at the moment. Otherwise, you can just proceed with the next class. Uh, I had this. I so yesterday I was saying this. How to find relative extrema of this function? The eighth question. So can does anyone have like any idea how to proceed?
So we are trying to find the maxima for this, is it?
Yeah, I mean it can be the maxima or minima.
Oh, sorry, extrema. Sorry, yeah. Okay. Mm,
Because there are like two variables x and y. So
yeah, we have to find a derivative, and then we can equate it to 0 and then perform the second derivative and then again equate to 0. I mean, that's a rough way to do it, but then we can find some critical point.
yeah, yes, yes.
And we can see
You
that.
can take the gradient. I mean the general uh, partial derivative with respect to x and y, and if you set to 0, you'll get some x and y values, right?
Yeah, and
Which
then
will depict, yeah, yeah,
yeah, sorry. So
and
then we can just say that whether it's greater than 0 or less than 0 and see where it is landing.
yeah, yeah, yes, yes. I mean, the only thing is like it's two variables. Like in one variable, it was like very clear. In two variables, you have to uh, take into consideration the Hessian matrix because, uh,
Correct.
yeah, yeah, okay,
Yeah, so I think that whole matrix itself is it's just a second derivative of the partial derivative. Basically, it's just a matrix of second derivative, no?
Yes. Yeah. So if second derivatives, again you have to see it's greater than zero, it's less than zero. But the second derivatives is like uh, there are four elements with respect to x twice, with respect to y twice, or with respect to x and then y. So you have to get uh, the determinant of Hessian. So determinant of Hessian can tell you if it's like positive, then the eigenvalues will be of same sign, and if it's negative, the eigenvalues will be of opposite sign. So that is also like one of the ways I think.
Yeah, I think that's a smarter way to do it.
Yeah. Yeah. So I think there are a lot of questions. So how do you want to proceed? Like, do we plan to do these questions in the week as well as read the chapter, or do you want to, because you should get the time also, right, to do everything?
Yeah, to do both, there's not enough time because reading the chapter only takes like a lot of time.
Yeah.
Yes.
And most of the times, the chapter reading also, you're not done by the end of the week because
Yeah.
some chapters are a lot of pages and it's not a straight read also. It's at every
Yeah.
topic you'll have to think about it, you'll have to figure it out what
Yes.
they're trying to say, right? Yeah.
Yeah, I think what we
I
can do.
mean,
Yeah, go ahead. Sorry.
yes. Actually, I was thinking like we can keep we can just solve questions without like preparing for them in the session itself, right? So we can give 1 hour for like discussions and 1 hour for solving like 3 to 4 questions or 5 questions, but good questions, so that we also get to brainstorm how to solve it. I mean, that is like one of the suggestions. Yeah, please go ahead. Like you're saying something.
Yeah, so I was saying the same actually. So what we can do is questions are there, so uh, everyone can put there and everyone can go through whenever their time permits. It's a continuous thing. It's not like like 2 weeks back I was reading about PCA. Today I was just reading. I felt that it was not written by me. So it's like we have to be in touch with all this. But I think during our this weekly session we can focus on chapters and maybe or if anyone have solved those questions we can and found one of the questions is little interesting, we can park, let's say, the last 15 minutes or 20 minutes every weekend where we will just solve some questions. We can even everyone can solve one particular question as you are suggesting, or if somebody found some question they want to explain it, that also we can do. But question and book both, I don't think we will be able to do it. But we can always do these questions offline based on our time. And during the session, we can park 10, 15 minutes or 20 minutes, whatever it is, half an hour to discuss some interesting problem.
Yes. I mean, like that brainstorming, right? Can the questions are the real uh, 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 they generate that momentum.
Yeah,
So
right. In fact, I
yeah.
added few questions where a few of the questions were actually we actually asked in one of the interview last week we had in our team,
Okay.
and so interestingly, so it was a panel. I'm just sharing. Okay, so it was a panel, and then one of the question, I thought that even if the candidate doesn't give the answer, that should be fine. But the other person in the panel, he was so sticky about that question that candidate has answered every question which was around his work, and he was a PhD. He was really good, but he failed to answer one very fundamental question. But we can sense that he was not in touch. So we were inclined, but that particular guy in the panel, he was a senior principal engineer, so he just declined based on that one question. It was very unfortunate for that candidate, but this is how people treat when it comes to fundamentals. At least in the industry, I've seen there are a few interviewers who just who are very specific to know the answer. I mean, they expect the answer to be exact in the format that they have learned. So, which is very bad. But the meta point is the questions. Few of the questions were very good. Like if you scroll up, there is one question about. I think it was about. Yeah, this one question on RAD that is about expectation. So this was one of the question below that. You can solve it later on, but that's a good question. Yeah, this one. And then there was one question. I have not mentioned this, but I can just share it. You can, I mean, they asked, you have a column vector and you are multiplying it with a row vector. So the first question was what you will get as an output. So the candidate said we will get a matrix. And then they asked what is the rank of that matrix. So he was trying to think about it and all that. He gave the answer later on, but the interviewer was expecting that it should be like this, like without without any uh, time. So yeah, so this question, and then if you scroll up in the linear algebra, there are few very good questions. That one this was not asked in the interview, but I just found it. Yeah, this one. This is the one. This question is also very good. 16th number question. So you can solve. I think these questions actually helps to clear the concepts.
Yeah, yeah, yeah. Great. So we'll do one thing in the next session. We'll try to keep some part of the session for questions. Even if you like have not solved, we can just discuss them and we just brainstorm on them a bit.
So which chapter we are going over next week?
So actually, yeah, actually, like, can someone take the constraint optimization? Uh, because I probably might miss the next session. It's like 50-50 right now. So
Okay, so I think we can then next week, and in fact after that also I might also miss. So and I think he will also be not there. Sujit, I think he's not here today as well. We can skip next week if we don't get the quorum. Otherwise, we can continue. Whatever everyone feels.
yeah, actually, I am applying for. I'm thinking of applying for PhD. So that is the reason I have like some stuff going on.
Oh, very nice.
But
Okay.
yeah. But yeah, I mean, like, if everyone is comfortable, we can skip next week and just proceed with the week after that.
Yeah.
I think the week after that, uh, we would be having parts of the fifth chapter as well. So for the questions part, we can do one thing, like we can solve the questions in the session itself, right? Even if we will upload it in the Google Doc. Whoever has a doubt or question, just upload it in the Google Doc, and we can just discuss them in the session, even if like we haven't solved it. We can just brainstorm on it, right? But so, how much do we want to cover till the next 2 weeks if we are planning to meet again after 2 weeks? The in the fifth chapter, I'll make sure the fourth chapter doubts are cleared because I was not able to give much time this week, but I will come back to them later and I'll clear all the doubts of the fourth chapter. Even I have a lot of doubts.
Next week is 17th, is it?
Yes, yes.
Oh, okay. Yeah, even I'm not sure about whether I'll be able to attend next week. But again, I'm not confirmed on that.
Okay. Yeah, I think then we can go for the week after that. But
Yeah.
but let's try to include uh, some theory of fifth chapter. What do you say? Or else do you want to? Because there are 2 weeks.
But then constraint optimization also has to be covered, right? Before fifth chapter
Yeah,
starts.
yeah, yes.
Okay.
Maybe you can do a piece of the fifth chapter. Fifth chapter is super long, but it's
Yeah,
Fifth chapter, every topic is a book. I don't
Every
know how many
topic
books.
is long,
yes.
either in content or in the number of pages. It's just a lot.
yeah.
I think
Sometimes
in
there's one line that takes you 1 hour just because you need to get some material elsewhere.
Right.
Yeah,
And then this is not something that we are trying to cover it on a week by week basis, right? So we're packing a lot of information in 1 week.
yeah, yes. And we need to revise also in between. I mean, as we go along.
Yeah, true.
Yeah. I think for the fifth chapter we can just go with the definitions that are there in the chapter. I mean, not into the logical parts, but just definitions like this means this means this. Like
Yeah,
what is
it's more
classification?
about explaining the model, like how it's built and everything. But if all of us are in this field, right, we already know all of that information. It's
Yeah, yeah,
talking about hidden units, why do we have so many layers, all those basic stuff, right? If we already know about it, we can just skim through that.
yes, yes, yes. So as I was like looking, the linear regression starts from page 104. I think we can do till that. Till that, I think only definitions are there. Like it's uh, like what are supervised algorithms, what are unsupervised, what is experience, what is performance measure, density, etc. So
Density.
yeah, density estimation, probability mass.
Oh, density estimation. Okay. Yeah.
Yeah, and yeah, we can. I will go through the doubts again. If you have doubts in KKT, please give that also. Write that in the doc. I will go through the notes.
So until where do we want to go?
I think 102, page number 103, before linear regression, example linear regression, which will be mathematical.
Okay.
So you're saying until that it's mathematical, is it?
No, linear regression would be the starting point of
Acha,
mathematics.
acha. Until that it's like just definitions.
Definitions.
Got it.
Yeah.
Yeah, definitions and formulae that we already know.
Yeah. So they are just like statements. We can just there, there's no much thinking in that.
Yeah,
You
maybe we
can read in that.
Yeah, I think we can like we have 2 weeks, so we will cover the residual whatever learning that we are pending, like constraint you said, right? And I've also not covered few of the things which you covered today, so we'll go through that.
Yeah.
And maybe for chapter 5, as Ratna mentioned, I think there are a lot of theory in the first place. So if we target till section 5.1, which covers linear regression, and we can stop till 5.1. Like 5.2 is capacity overfitting, underfitting. We can do that late next, but till 5.1 we can target if we can cover till linear regression, because before linear regression is all theory is what I can see when I just scroll.
Yeah.
So at least linear regression,
Yeah.
so we'll feel that okay, we have completed something substantial, like in that sense.
Yeah. I mean, that is also fine with me. I mean, because linear regression also, like most of us would be in somewhat familiar, and it won't be that tough also,
Right,
I
right,
guess.
right.
Yeah, it's basics.
Correct. Okay.
Cool then. Okay. So we'll meet after 2 weeks then. Great. So any doubts and any other questions, if you find interesting, please upload them in the Google Doc. And any other suggestions if you have for this uploading questions, because as Andrew was mentioning that edits are taking, like, because if you just delete something, you won't get the chance to delete. Uh, it would be taking a lot of time.
Yep.
So
Yeah.
yeah. So if you have any suggestions, do let me know. And then yeah, then that's it. We'll wrap up this session. And happy weekend, everyone.
I think Andrea has something to say.
No, I'm okay.
Okay.
Yeah, Andrea, you suggested this tool for equations, right? Uh,
I suggested what?
writing equation.
Writing
Uh,
equation.
That
Yeah,
like,
typist. Yeah. It's you know LaTeX,
yes,
so it's kind of
but can we put our questions there? Like, can that be used for that purposes instead of Google Docs?
yeah, it's better for equations. You can write it in line
yeah, you don't need
using
to click.
anything.
Like if you want to write a gamma or delta or something, you just write you know anti / gamma and then it gets compiled.
Okay.
I don't
But
know.
how
I've
about the
never tried. I just know it's super new, and so I've
okay?
never. I have a colleague that uses it. I know you can do. Um, the thing is open source, but the you have the collaborative stuff and you have the pro version or whatever. But I think you can do collaborative stuff on the online version. I'm pretty sure, but I haven't. I've never tried it
Okay. Otherwise,
on collaborative. I have tried it on some documents for myself. I can also download the stuff. And
okay. Yeah,
I
I'm
can
like
I don't know. I can try. I
I
can
was
send you a
more
link.
Yeah, sure, sure. Yeah, I'm like more interested in collaboration part because in Google Docs, otherwise I can just give everyone the editor access and take snapshots some at
Yeah.
some uh, after some periods. So that is also one of the things you can do.
Mm.
And for equations, you can also do use the screenshot feature.
Yeah.
Is
I'm happy to
something
try.
like, sorry, go ahead.
No, no, go on, go on.
I was just wondering if something like Overleaf is collaborative, can we use it?
Yeah, I
It's
think it is
like
collaborative. I've used it. I mean, as a team, we have used it for
Then we can
collaboration. But
use Overleaf only, right?
yeah, is everyone comfortable with LaTeX? Because we would have to write everything in LaTeX. Uh,
I have little experience. Yeah, I have used it before, but yeah, let's ask others as well.
Yeah, I
I
think
am,
because
but yeah, I don't know if others are.
only thing with overleaf is that we cannot, and it's difficult to just copy paste. Like if we want, we can just take screenshot of the question and just paste
Oh,
it, which is a very fast feature in Google Doc.
okay.
But
Yeah, I mean, then it's
yeah,
fine. I think for something this small, we don't need to go for a LaTeX editor. Maybe let's just stick to Google Slides.
yeah, but I
yeah,
think yeah, I think we can, Ratna and Amit. I think if I this is something that I also wanted to learn. So whenever in future, if you get some time, if you can just run through that latex, how to work with that, maybe 10 minutes, that would be very helpful. This is it's just a meta learning, nothing to
Hmm.
do with it, but it would be very helpful. Yeah,
Yeah, I
yeah,
actually like LaTeX.
yeah.
yeah. LaTeX is for reading purpose. It's like really good and it looks
Yeah.
really nice.
Even during my university, all documents and everything, right? We used to write in LaTeX only, presentations, documents, everything, because it's cleaner, easier, and most people write in LaTeX only, research work and everything.
Yeah, it's actually very fluid. Like I was attending someone's lecture some time back, and he was doing it in a notebook with some I think some connector or something, some library he has connected, and he was writing equation like just like how we type in the key on the keyboard, and my full focus for the whole session was how he could do that, and by the time his session was over, so I could not focus on the session. I was so blown away by how he was typing. So if you can share that, that would be great. Yeah,
Yeah, we can do that.
Okay.
thanks.
Yeah. So yeah, we'll look at platforms like Overly for the one which Andreas mentioned, and we can go ahead with that also. Yes. Okay. So let's wrap up this session and let's meet on I think 24th
Okay.
and with I think 5.1 till 5.1, right?
Yeah, you can try. Okay.
Cool, cool. Okay. Enjoy your weekend. Thank you.
Thank
Bye
you.
bye.
Thanks, everyone.
Thank
Bye.
Thanks.
you. Thanks, everyone.